Hello, I am Ahmad, and this video is about introduction to plastic bending moment calculation. It is not about bending moment directly, but it's the concept of how we can calculate and understand better a beam is under bending and the bending is increased, how the cross section would become plastic. Let's calculate it. Assume we have a rigid element which is supported by a hinge support at point A. Rigid element. And we have 6 rods connected to this element. All rods are with the same length. And the spacing between the rods is also the same. A. And let's name these points. Point B, C, and D. B prime, C prime, D prime. And let's apply a load at furthest distance from the center of the beam, E and E. The same value in the opposite direction. If we look at this beam and if we apply the force, so two P's which are called couples, they are trying to rotate the rigid element counterclockwise. As a result, the rods in the left side of point A will be under tension and the rods in the right side will be under compression. In this example, let's assume that elements are short enough and buckling would not happen. Let's assume A is 100 millimeter. So some other assumptions. It is the material is elastic, perfectly plastic, with sigma y equals to 200 megapascal, or let's go with 250. So 250 megapascal and modulus of elasticity of 200 gigapascal. We can sketch the stress strain diagram. Sigma y and epsilon y. So epsilon y will be sigma y divided by E, 250 divided by 200 gigapascal, so it will be 0.00125. As far as the element, the horizontal element is rigid, when it starts to rotate about point A, it will not be distorted. As a result, we can use the proportional displacement of element B, C, D and B prime, C prime, D prime. So first of all, let's calculate some basic requirements. Sigma y is 250 megapascal, and let's assume that the rods are with the diameter of 25 millimeter. Area of the element will be pi d squared divided by 4 pi 25 millimeter square divided by 4, 491 square millimeter. Sigma equals to F divided by A. As a result, the yielding force will be sigma times A. Sigma is 250 megapascal times 491 square millimeter. So it is 122.75 kilonewton. And also we can calculate what is the corresponding yielding deformation. We can do it in two ways. Identical answer. Delta y equals to Fy L divided by AE. So Fy is 122.75 kilonewton. The length of the element is 500 millimeter. Area is 491 square millimeter. And modulus of elasticity is 200 gigapascal. So it is 0.625 millimeter. Or as far as epsilon is delta divided by length, we can calculate delta y times L times epsilon y. So L is 500 millimeter times 0.00125, which is 0.625 millimeter. So we can sketch another graph for this element, which is identical for all members, for all bars. And here we have delta y, which is 0.625 millimeter, and corresponding force, which is 122.75 kilonewton. Force and delta. Here also I have to write the units. So it means that if the load in one of the members reaches to 122.75 kilonewton, after that it is plastic and there is no resistance to take any more load. As a result, if there is any action in other rods, that yield member would start to deform without any resistance. So in other words, it is ignored or eliminated from the system. Now let's sketch the free body diagram of the rigid element. At point A, we have AY and AX. At both ends, we have force P, the same value in the opposite direction. And as we mentioned, we would expect here we have FB, FC, and FD. And in the other side, we have the same values in the opposite direction. We know that there is no horizontal force in this case, and AX is there just to keep equilibrium and solving the equation. And as far as the system is symmetric, then FB is expected to be as same as FB prime if the material is homogeneous and it behaves the same way in tension and compression. In this example, we assume that we are dealing with a material which its behavior is the same in compression and tension. If we apply the load, then the rigid element starts to rotate about point A. So we would expect that this deformation is achieved. I can sketch it separately, that it is easier to follow. And it is exaggerated. Delta B, delta C, and delta D, delta D prime, delta C prime, and delta B prime. So now we want to write the compatibility equation from the similar triangles. So delta B divided by 3A is the same as delta C divided by 2A and delta D divided by A. And we can cross A and write the equation as delta B equals to 3 delta D and delta C equals to 2 delta D. So this relation between delta B and delta C and delta D is called compatibility equation, and it is valid regardless of one or more member become plastic or in the elastic state. Similarly, we can write the same equation for the right side of point A rods, delta B prime divided by 3A, delta C prime 2A, delta D prime A. And then delta B prime will be 3 times delta D prime and delta C prime 2 times delta D prime. And also we can write the same relation between delta B and delta B prime. We will get delta B is as same as delta B prime, delta C is as same as delta C prime, and delta D is as same as delta D prime. These are compatibility equations and they are valid regardless of the behavior of the element, because we are talking about the rigid horizontal element which is rotated for an angle, and then the rods will follow the deformation. Now, what would happen if we increase the load? As far as the furthest points, B and B prime are going to have the maximum deformation, so it means that they are taking more load than other elements. As a result, they will yield first if we increase the force. So we would expect that B and B prime would yield before C and C prime, and C and C prime would yield before D and D prime. So the sequences of yielding in this example is B and B prime, C and C prime, and finally D and D prime. Now in each step, we are going to calculate what is the maximum force of P that we need to apply until one or more member of these bars become plastic. So first of all bars in elastic phase. So it means that when we say elastic phase, it means that the elastic equation is valid. So elastic equation is valid in terms of the rod is under axial force. As a result, the deformation can be calculated based on the equation of FL over AE, which is valid only in elastic phase. So delta B will be FB times L divided by A and E, and so on. Delta C FCL AE. These equations are valid only if the system is elastic. If one of them is not elastic, then we have to remove that equation for delta calculation. Now we have the free body diagram. Here is AY, E, E, and here we have FB, FC, and FD. Similarly, FD prime, FC prime, and FA prime. And we know that the first member that would become plastic or yield is B and B prime member. And we calculated Fy earlier, and Fy is 122.75 kilonewton. In other words, when we increase the force P, then we expect FB and FB prime yield first. So now we can calculate what would be the force in FC and FD by the equations that we determined based on the compatibility equation. So let's name these equations as set 1 or set I. From set I equations, we know that delta B is 3 times delta D. And as far as the elastic equation is valid, we can write FBL over AE is the same as 3 times FDL over AE. So FD will be 1/3 of FB. As far as B is now plastic, or it yields, then FD will be 1/3 times 122.75 kilonewton. It is 41 kilonewton. Also, delta C was 2 delta D. FC times L over AE is the same as 2 times FD L over AE. The same length, the same area. As a result, FC will be 2 times FD, and then FC will be 82 kilonewton. So if your assumption is not correct, then you can check at this point. When you calculate other rods, they should be less than Fy. 122.75 kilonewton. This is valid. 122.75 kilonewton. This is also valid. It justifies that your assumption that FB and FB prime would yield first is valid. So you don't need to assume something else. But for example, if you have different material, different length, different yielding force, perhaps it would affect your calculation. You assume that FB is plastic first, and then here you can see that FD is greater than yielding point, but it's not the scope of this example. Let's move on. This is valid, and we can go to the next phase. So point A, and according to our calculation, now the force at point B will be 122.75, and then this will be 82 kilonewton, and this will be 41. The same concept for the other side will result in the same value, but in the opposite direction. And the target is calculation of force P. We can take moment by respect of point A. So it will be E times 3A plus P times 3A minus 122.75 times 3A, but times 2 because we have two sides. You can see from the first two terms, they are the same. Minus 82 kilonewton times 2A, again times 2, minus 41 kilonewton times A times 2 equals to 0. From here, we can calculate P, and I name this force as P1. So it will be 191 kilonewton. So it means that when we are increasing the load, P, if it is less than 191 kilonewton, then the system will be completely in elastic phase. None of the rods would yield. Now let's calculate what is the deformation at point B in this stage. As far as F at point B is Fy, which is 122.75 kilonewton, delta B will be delta Y. And we calculated it earlier, and it was 0.625 millimeter. Sigma at B is also sigma Y, which is 250 megapascal. And epsilon at B will be epsilon Y, and it's 0.00125. So for element B, we are exactly at the point that after that it cannot take any load. Here we can calculate also the sigma in other members and also the strain and deformation. For element C and similarly C prime, Fc is 82 kilonewton, and delta C will be FL over AE, so it will be 82 kilonewton times 500 millimeter divided by 491 square millimeter times 200 gigapascal. So 0.42. Sigma also is F divided by area. It's a proportion of 2/3, so it should be 2/3 of 250. 82 kilonewton divided by 491 square millimeter. So it will be 82 kilonewton, 491, and it's 167. And also epsilon will be sigma over E, or you can calculate delta divided by L. It doesn't matter. So 167 megapascal divided by 200 gigapascal. Also, we can apply the same procedure for element D and similarly for D prime. Fd is 41 kilonewton. So delta at D will be 0.21 millimeter and sigma will be 83.3 megapascal and epsilon will be 0.00042. That's the first step. So the element is rotated until P is 191 kilonewton, And at this point, two elements which are with the furthest distance from the center would yield, and the others are still in the elastic phase. Now we can sketch the graph for force displacement and stress strain for three elements: sigma and epsilon, megapascal, millimeter divided by millimeter, force, kilonewton, and delta, millimeter. In sigma graph, this is 250, and the corresponding strain is 0.00125. In force displacement, force is 122.75 kilonewton, 0.625 millimeter. Now, this graph represents B element. For B element, we are at this point. (250 megapascal corresponding to 122.75, and the deformation at point B is 0.625. For the other element, element C, we are in the 2/3. So we calculated it was 167. With 84. And the force was exactly 2/3 of 122.75. 82 kilonewton. And it was 2/3 of 0.625, 0.42 millimeter. And also for the other element, D, 83.3 kilonewton, corresponding to 0.0042 strain, and 41 kilonewton, 0.21. When the force is increased to 191 kilonewton. It is deformed and this deformation is 0.625. This deformation is 0.42 and the other one is 0.21. The same in the right side of A. When the force P is P1, which is 191 kilonewton. We calculated it earlier here, so which is called P1. Now, if we look at the strain of each element, so strain in this element is 0.00125, and here This is 0.0084 and the other one 0.0042. So element B and B prime are now in their yield limit of deformation. So it means that from now on, if the load is increased, they are not taking any load. So the easiest way to solve this type of questions is that we can sketch a field line for those elements which are still in use and just have the dashed lines for those elements that from now they are eliminated. So I sketch my new structure. It means that the load is 191 kilonewton and now two elements are eliminated. They are not capable of taking more load. So we can assume that they do not exist. And from now on, they just elongate. So what do I have? I have the rigid element. It is not horizontal anymore. But for solving the question, it's fine if we assume that the rotation is very small. So now I write down that this is delta P1. So we have P1, which is 191 kilonewton, and then we want to see how much load we can increase in the system. I sketch the dashed lines for the members which are not working anymore. So these are B and B prime which are not in use. And here I can sketch the other elements which are still in their elastic phase. C, D, D prime, C prime. So here we are going to calculate what is the delta P1 if we can increase the load. It should not be forgotten that now C, D, C prime, D prime are pre-stressed. Already we have some part of load in their cross section. So let's write down what is the force at C. At C, the force is 82 kilonewton. And F at D is 41 kilonewton. Now, what is the capacity of element C? Capacity left for element C. So it can take up to 122.75 kilonewton, and it is already loaded with 82 kilonewton. So we have 40.75 kilonewton capacity left for element C. And the same for element D, 122.75 minus 41 kilonewton. So it will be 81.75 kilonewton. Here we can see that element C and C prime are with the minimum capacity until they become yield. So if we increase the force, then C and C prime will yield first. Now we are going to calculate what is delta P1 in order that these two elements yield. I'll sketch the free body diagram. Delta P1, delta P1, delta FC1, delta FD1, and then delta FD prime 1, delta FC prime 1. So here we can see that we do not sketch anything for B and B prime. They are now in their plastic phase and they cannot take any more load. Now delta FC1 is 40.75 kilonewton. We can assume C and C prime become plastic before D and D prime. So if this is valid, then the maximum force that we can apply on C and C prime is 40.75. Again, we need to come back to our compatibility equation. As far as C and D are still in their elastic phase, we can also apply the elastic equation. So from set 1 or set I, we know that delta C is 2 times delta D. As a result, Fc times L divided by AE will be 2 times Fd L over AE. So delta Fd1 will be delta Fc1 divided by 2, and it will be 20.375 kilonewton. And here we can see that it is, you shouldn't check with the 122. You have to check with the left capacity of the relevant element. So it should be checked with 81.75 kilonewton, and this is fine. So it means that our assumption is valid. So now we can just make a simple bending moment equation, delta P1, and here this will go to 40.75, and the other one is 20.375, and here is point A, that we can make the bending moment equilibrium equation. Delta P1 times 3A times 2 minus 40.75 kilonewton times 2A times 2 minus 20.375 times A times 2 equals 0. So delta P1 will be 34 kilonewton. That means if we increase the force in the system from 191 with 34 kilonewton more load, then 2 more elements will yield, which are C and C prime. So at this point, we can calculate what is the deformation at point C. So force at C will be force at C with the first iteration plus delta force at C that we calculated here, which is in total 122.75 kilonewton. F at D will be Fd at first increase plus delta Fd1, which is, it was 41 kilonewton plus 20.375. So it will be 61.375 kilonewton. As far as this is in the yielding limit, delta at point C will be 0.625 millimeter. And here we can calculate what is delta at point D. It's in elastic phase, so FDL over AE, and it's 61.375 kilonewton times 500 millimeter divided by 491 square millimeter times 200 gigapascal. So it is 0.3125 millimeter. We can see that the compatibility equation is valid. Delta D should be half of delta C. But what happens to element B? So element B and B prime, F at B cannot be increased, so it is constant, 122.75 kilonewton. But as far as the compatibility equation is valid, we can calculate the deformation at point B. So here we can see that delta B needs to be 3 times delta D, and it will be 0.94 millimeter. Also, strain is beyond the yield strain. So epsilon will be delta divided by L. Here you cannot calculate epsilon is not sigma over E anymore. This is not valid. Because now we are not in the linear phase, or we are not in the elastic phase. So 0.94 millimeter divided by 500 millimeter. So it will be 0.94 divided by 500. It's 0.00188. And we can see that epsilon y was 0.00125. So this is greater than. And also here, this is greater than delta y, which was 0.625 millimeter. Now we can sketch the situation for three elements. I start with the element C, which is now in its yielding point. C is here. It's taking maximum or yielding load, which is 122.75. And now the load in D element is 61,375. So it will be 125 megapascal corresponding to 0.000625. And here it will be 61.375 kilonewton, and the deformation is 0.3125 millimeter. Element D, and also element D prime. And now we know that the element B deformation is 0.94 millimeter, so it will be somewhere here. And also S-strain we calculated, and it was 0.00188. And now we can calculate what is the force at this stage that we applied to the system. So P, let's say P2 is going to be P1 plus delta P1, 191 kilonewton plus 34 kilonewton. So it will be 225 kilonewton. And we can see that in our graph, B and C now are in their maximum yielding limit. And from now on, if there is any capacity, only element D and similarly D prime would take care of the system. Up to now, we can summarize our calculation. When P approached to P1, 191 kilonewton, deformation at point B was 0.625 millimeter. And when P approached to P2, 225 kilonewton, delta at point B was 0.94 millimeter. Do we have any capacity left? For sure we have, because still we have two members, D and D prime, that are with 125 megapascal stress and 61.375 kilonewton. But C and B are now eliminated. So now we can sketch the rod for the third part, or for the third phase. And we can write this as delta P2. And as far as B and C are now in the plastic phase, we can just use dash lines for them. So it means that they are not collaborating to take any load. But the other two elements, they are still in the system, a D and D prime. So, but they are loaded. Already they have F at D is 61.375 kilonewton. So what is the maximum load that they can take? Delta FD now number 2 is 122.75 kilonewton, which is the maximum load that they can take before they become plastic, minus 61.375 kilonewton, and it is 61.375 kilonewton. Now we can write the bending moment equation by respect of point A. So delta P2 times 3A times 2 minus delta FD2 times A times 2 equals 0. And the maximum value of this delta FD2 is 61.375 kilonewton. As a result, delta P2 is 20.5 kilonewton. So we can still increase the load by almost 20 kilonewton. Now we can calculate what is the situation for deformation of the elements. Now FD is 61.375, which is coming from FD plus delta FD1 plus 61.375 kilonewton, which is coming from delta FD2. Now it is 122.75 kilonewton. And now delta D should be 0.625, or epsilon D should be yielding strain, which is 0.00125, and sigma D should be sigma Y, which is 250 megapascal. For the other members, now for C and B, FB is 122.75 kilonewton. It cannot be more than that. Also, C became plastic earlier, so it is 122.75 kilonewton. But delta B and delta C cannot be calculated according to elastic equation, which is FL over AE. We need to calculate the deformation based on the compatibility equation. So delta B was 3 times delta D. So it will be 3 times 0.625 millimeter, 1.875 millimeter, and corresponding strain, you cannot use sigma divided by E. It will be delta divided by L. So it is 0.00375, and you can see that it's greater than 0.00125. Also, delta C from the set I equations, 2 times delta D, 2 times 0.625 millimeters, so it will be 1.25 millimeter, and epsilon delta divided by L, so it is 0.0025, which is greater than yielding strain. We start with point D. Now D is here in the yield limit, and B is 3 times bigger. One 1.875 millimeter, and C is 2 times bigger than D. And we calculated delta P. It was 20.5. So now P at this stage, let's say it is P3, is P2 plus delta P2. So it was 225 kilonewton plus 20.5 kilonewton, which is 245.5 kilonewton. So 3 steps and corresponding deformation delta at point B here will be 1.875 millimeter. Now we can sketch the original rod at the final stage because there is no more element that they can take the load. Element B, element C, element D, element D prime, C prime, and B prime. So if we increase the load to 245.5 kilonewton, then the deformation of this system will be in such a way that here we have 1.875 millimeter deformation, and here we have 1.25 millimeter, and here we have 0.625 millimeter. The same in the other side of point A, 245.5 kilonewton. And the force in each element now is Fy. We can see that at this point, the system does not have any capacity left to take more load. So this load is called the maximum load that all rods connected to this rigid element become plastic. And this load is also called plastic load. It means that what is the load that the whole system approaches to a level that there is no capacity left. So from this moment, this system is called mechanism, meaning that there is no capacity left for equilibrium and the whole system is now plastic to deform. In other words, if you increase the load, then it moves and it cannot be in a static equilibrium. What is needed to know: if we are assigned to calculate the plastic load, you do not need to go through this journey. You can just put all the loads at their maximum value and then you can calculate the maximum load. For example, if we are assigned to calculate, determine the plastic load of the shown system, with the given information, and assume that this is exactly the same question, but we are not going to calculate a step by step. So you have 3 rods in the left, 3 rods in the right, and you are going to calculate what is P plastic. So P plastic means that all of the members would become plastic or in their yield limit. So then you need to write only one single equation, sigma moment about A equals to 0, and it will be P plastic times 3A times 2 minus 122.75 times 3A times 2 minus 122.75 times 2A times 2 minus 122.75 times A times 2 equals to 0, and then you can easily calculate the plastic force. So it is 245.5 kilonewton. And we can see that it's exactly the same value that we calculated step by step. And the most important graph in such cases is the force and its corresponding deformation for the point that you apply. So this is P in kilonewton, and deformation at point P, which is the same as deformation of point B in this example. So when the load is 91, 1, 2, 3, 4, so let's say this is 191, I assume that this is 25 kilo. then deformation was 0.625. And up to here, it is completely linear. And then when the load was 225, then deformation was 0.94. 6394, somewhere here. And then when the load is 245.5, the deformation is now 1.875. So here we can see that the deformation is accelerated by increasing the load. And from here, the system is called mechanism, meaning that there is no resistance. And this load is called elastic load. And the minimum load, or the value that the first element would yield, is called elastic load. So these are two main important definitions of elastic and plastic load. Now, if we look at the system, if you have such a member which is supported by a hinge in the center, and assume that we have many rods connected to this system. Now, if you apply a moment about the center point, what would happen to the system? So first of all, the furthest elements would yield. So this is Fy or sigma y. Let's go with stress. Then from here, if we increase the load, sigma in the first and last element cannot be increased. They will remain constant with sigma y. We calculated the same example with 3 rods in each side. So then you can increase the moment until the next rod yields. So what would happen? Then the next phase is we increase the load in order that the next element will yield. And then we can increase the moment. The second furthest elements are now plastic. The stress in those elements cannot be increased. Now it goes to the next one, and the next one, and the next one, and so on. So then the next one, then very close to the center. So here is the concept of how a cross section under bending moment would start to yield first, and gradually it is in its plastic capacity. So when all the fibers, all the rods in both sides are now plastic, then the moment is called plastic moment. We will go through this in more detail, and also how to calculate accurately in the other video. And this was just the concept of how to calculate the plastic force for a rigid bar connected to different rods. Yes, so we went through the calculation of plastic force for one horizontal rigid element in this video, and we talked about how we can increase the load until the system is not in equilibrium. If the elements are with the perfectly plastic material. This is a very good example to understand how to calculate the plastic bending moment, which will be covered in the next video. Thank you for watching, and see you next time. Bye.